To test if gravity is a quantum phenomenon, we don't need to observe a black hole. We can test it in a laboratory using two microscopic masses. This is the BMV experiment. By placing these objects in a quantum superposition, researchers aim to observe exactly how they warp the local gravitational field. If the gravitational field itself is a quantum entity, it will force these two superposed masses to become entangled. Their positions will become mathematically intertwined, reacting to each other instantaneously. In a classical universe, each mass produces a single gravitational ripple, but in a quantum superposition, each mass exists in two locations simultaneously. This generates four distinct overlapping gravitational ripples that lock the entire system into an entangled state. Measuring this entanglement would definitively prove that gravity obeys the laws of quantum mechanics. But this physical measurement comes with a severe limitation. It proves that gravity is quantum, but it provides no mathematical framework for how it functions. We currently lack a unified equation capable of describing the phenomena these laboratories are racing to measure. The laboratory can confirm the existence of quantum gravity, but finding the exact mathematical language to describe it requires navigating significant theoretical obstacles. One prominent attempt to write this language is asymptotically safe quantum gravity, or ASQG. It aims to solve the problem purely through the established rules of quantum field theory. ASQG operates under strict mathematical axioms. It must be a UV complete theory, meaning its equations remain valid at high energies, and it must contain exactly a finite number of quantum fields. Opposing this rigid field theory approach is a different set of principles, the swampland program. The swampland establishes a set of bottom-up consistency bounds, like the absence of global symmetries, that any valid theory of quantum gravity must obey. Fail to meet these criteria, and the theory is relegated to a landscape of mathematically inconsistent ideas. This diagram maps the theoretical landscape. We have the territory claimed by string theory, the region defined by asymptotic safety, and the narrow intersection of mathematically consistent theories where a true description of quantum gravity should reside. The swampland defines strict borders based on the behavior of black holes and holography. ASQG attempts to map its own route into this consistency circle, using only the geometry of pure field theory. The mathematical requirements of these two frameworks point toward a significant structural conflict. If gravity is described by a pure field theory, it must be able to function without the specific consistency rules that define the swampland program. The first major fault line between these frameworks lies in the kinematic constraints of space-time geometry itself. The swampland relies on a tightly woven web of logical dependencies. To prove a theory lacks global symmetries and possesses a complete charge spectrum, the math relies on holography, which depends on space-time topology change. This foundational pillar assumes space-time can fluctuate, tear, and stitch itself into structures like wormholes. But within a strict quantum field theory, forming a wormhole is mathematically prohibited. The structural geometry cannot break and reconnect. Quantum fields are defined exclusively on a fixed continuous space-time manifold. They are operator-valued distributions bound to a specific, unyielding topological background. This creates a direct structural incompatibility. The continuous path integrals required by quantum field theory cannot mathematically sum over fluctuating, changing topologies. Forcing topology change into these equations generates severe global obstructions. It yields infinite statistical weights from invariants like the Gauss-Bonnet term, causing the math to fail. If we adhere to the strict rules of asymptotic safety, we have to look at what happens to the swampland's requirements. When we sever the connection to topology change, the holographic principle loses its mathematical grounding. Stripping away topology fluctuations to satisfy a pure field theory eliminates the swampland's primary proofs for holography and the breaking of global symmetries. Without topology change, the swampland must rely entirely on the thermodynamics of semi-classical black holes to enforce its consistency bounds. This means extracting mathematical limits from the way a black hole processes information and entropy at its event horizon. However, asymptotically safe gravity has its own strict requirement here. Its high-energy scattering amplitudes must exhibit scale invariance, scaling as a power law. This contradicts asymptotic darkness, the expectation that the high-energy spectrum of any gravitational theory is dominated by the formation of large black holes. This graph illustrates the conflict. The bottom curve represents the power law required by quantum field theory. Rising above it is the super exponential curve, representing black hole density of states. At high energies, the black hole microstates massively overpower the field theory parameters. This super exponential scaling breaks the Callan-Lehman integral representation, which is a structural necessity for defining a canonical partition function in any field theory. A mathematically consistent quantum field theory of gravity requires us to abandon the standard thermodynamic interpretation of black hole microstates. Moving past kinematics, the conflict becomes even more pronounced when we examine the dynamic limits of these frameworks within what physicists call theory space. Theory space is a geometric map parameterized by the physical couplings and moduli of a given system. By pushing parameters to their infinite edges, we test the theory's extreme limits. At these distances, information theoretical factorization occurs, where degrees of freedom decouple. Because gravity couples universally, this factorization means the gravitational force itself must decouple entirely. To accomplish this, the swampland distance conjecture mandates an infinite cascade of new particle species, driving the effective gravitational cutoff to zero. This infinite cower of particles crashes into the defining axiom of asymptotic safety. The theory must contain exactly a finite number of quantum fields. If the number of fields is strictly finite, the mechanism required to drive the gravitational cutoff to zero simply does not exist. Asymptotic safety dictates that theory space must be finite and compact, which would outlaw the infinite horizons demanded by the swampland program. Forcing gravity into the framework of field theory requires abandoning several foundational principles that have defined the study of black holes and space-time geometry for decades. Looking back at our theoretical landscape, the intersection where these ideas might coexist is exceedingly narrow. If swampland consistency rules are a universal truth, asymptotic safety cannot be a fundamental theory. It only exists as a low-energy approximation. Conversely, if asymptotically safe quantum gravity is the fundamental law, then reality operates without fluctuating spacetime, without black hole microstates, and without infinite particle cascades. Theoretical physics has reached a mathematical deadlock, where leading frameworks for understanding the universe have proven to be mutually exclusive. This brings us back from mathematical abstraction to the physical laboratory. Experiments like the BMV proposal aim to force a physical post-selection of entangled quantum states, relying on macroscopic measurements rather than competing equations. These measurements will eventually compel reality to reveal which theoretical rulebook it actually follows. When mathematical models reach the limits of understanding, physical observation remains the only tool left to anchor the landscape.